Hello everyone, welcome to this lecture. In this and the next lecture, we are going to talk about another application of the model obtained by experimental model analysis, and that application is finite element model validation and updating. In this lecture, we will focus our attention on finite element model validation. So, first we will talk about what is finite element model validation, what is the need of finite element model validation, and what are the sources of possible inaccuracies in an FE model. And then how to correlate the predictions of the finite element model with the results of model test. And then we will look at what is model reduction and mode shape expansion. So, let us first of all talk about what is model validation. So, model validation is the process of confirming that the model can accurately predict the system's dynamic behavior for the intended application. So, in the finite element model, for whatever purpose it is to be used, we would like to check whether it is accurate enough to make predictions for that application. So, verification and validation of a computational model, they are necessary steps to be carried out before the model is used. So, in industrial practice, the verification and validation of the model have become very necessary steps before the model can be used. And what is model verification? So, the verification is done to confirm that the computational model is a good numerical approximation of the continuous mathematical model. So, generally we use discrete models to analyze a system. For example, finite element model or some other numerical model is a discrete representation of the continuous system, right. So, in the model verification, it is checked whether the discretization error associated with the discrete model is negligible. So, we like to ensure that the discretization error is small. Verification also involves checking the validity and correctness of the codes and algorithms that are used to ensure that they are error free. So, verification is the first step of checking the model. The next step is model validation, which involves now comparing the predictions made by the FE model with some reference data identified from the test. So, therefore, the validation is based on comparing the model's prediction with those obtained from the relevant tests conducted on the system. So, for purpose of validation, we require some reference data against which the FE model predictions can be compared. So, by comparison, then we can arrive at a conclusion whether the FE model is accurate enough in making the desired predictions. So, let us now look at what is the need for FE model validation. Are there any sources of possible inaccuracies in FE model? Let us try to discuss that. So, the first phase in the finite element modeling is to make a solid model of the system. So, are there any inaccuracies which might be associated with solid modeling phase? So, in the solid modeling, generally the geometry can be accurately modeled based on the available drawings, right. However, some uncertainties may be associated with this phase when the geometric simplifications are made or idealizations are done. So, many times some complex geometry may be simplified to provide ease in the modeling, and some idealizations may be done. So, therefore, these geometric simplifications or idealizations may introduce modeling inaccuracies in the solid modeling phase. Now, inaccuracies may also be associated with material properties that are used and models of, let us say, various joints which are there in the system. There may be inaccuracies associated with those models. So, material properties are generally based on standard material databases, and inaccuracies may be there because the actual material properties may have some deviation from the standard values of the material properties. In some cases, the material properties might not be correctly known and some approximations may be used. So, that again may be a source of inaccuracy in the material properties that are used, and material properties strongly affect the predictions of the model. Many systems have a large number of joints and different types of joints like bolted joints or riveted joints or spot welds. So, therefore, if each joint has to be accurately modeled, then the model size will become very large. So, therefore, generally what is done in order to keep models size manageable, the joints models are simplified. So, one approach could be that the joints are completely ignored, right. They are modeled as if the structure is continuous, there is no joint. That is one probably the simplistic approach. In other cases, some simpler models are used to model the joint, and such simpler models may be associated with some parameters which define those models, and the values of those constants may be unknown, right. They may be uncertain. Often the damping in the FE model is taken as a proportional damping model in the absence of accurate model presenting the damping. So, that is a source of error. Also, in proportional damping model, values of the proportionality constants, they are generally not correctly known, right, and therefore, their values again are uncertain and a source of modeling inaccuracy. So, boundary conditions could be another source of inaccuracy. So, often ideal boundary condition like fixed, free or simple support is assumed, but the actual boundary condition may be different, leading to inaccuracies. For example, if a structure is fixed at certain points, so the actual boundary condition may deviate from that. There may be some flexibility associated with those points. Those points may not truly have zero displacement, right? They may have some small movement when the structure is loaded. So, therefore, in the model we may assume it as fixed, but the actual boundary condition is different from that. So, that is a source of inaccuracy, and boundary conditions also affect the dynamic characteristics a great deal. So, these are possible sources of inaccuracies in an FE model, because of which the predictions made by the FE model may deviate. So, now the question is, what is the data against which these predictions can be compared, so as to determine to what extent they are inaccurate. So, let us talk about what could be the reference data for FE model validation. So, the output of experimental model analysis can be considered more accurate than the FE model predictions. So, this is because the experimental model analysis or model test is conducted on the actual structure or the actual prototype of the system. So, therefore, the test takes into account all the effects which are present in the structure. For example, the actual material properties, the actual boundary conditions, the joint characteristics, the damping that is present. So, everything is taken care of when the test is done, right. So, all these characteristics of the system, they affect the test data. So, whatever measurements we take, they take into account all those effects, and hence we can consider the experimental model analysis results to be a good representation of the dynamic characteristics of the structure or the system. One may say that there may be some noise that is generally associated with experimental data like a model test. So, then how that can be considered as accurate? So, the point is that model test results we obtain from the experimental model analysis, they are accurate, but they may be a little bit imprecise because of the noise that might be present. But this noise which is there, which causes some variability of the measurement, so that is random in nature. So, that noise which is there from measurement to measurement, that small variation is due to the random variation in the measurement, right. So, there is some random noise that may be associated, and this random noise can be reduced by the process of averaging. So, we can obtain an accurate estimate of the true characteristics by the process of averaging. So, therefore, the model test data is accurate, though it may be a little bit imprecise. However, the FE model predictions may be associated with some inaccuracies, as we discussed on the previous slide, and therefore, they are not supposed to be as accurate as the test results. They may be precise. So, we may calculate the dynamic characteristics to a good precision, right, but they may not necessarily be as accurate. That is why if we want to now compare the accuracy of FE model predictions, then they can be compared against the model test data. And that is why the model test data is used as reference data for determining the accuracy of the FE model predictions. So, now what is FE model correlation? So, FE model correlation is quantification of the difference between the predictions of the FE model with the model test data. So, this difference, quantification of this difference is referred as FE model correlation, that how much or to what extent the FE model predictions correlate with the model test data. So, that is FE model correlation. Now, how FE model correlation can be done? So, therefore, the comparison quantifies the degree to which the FE model predictions correlate with the corresponding data from the test, and this indicates the level of error in the FE model predictions. So, now the question is, what characteristics should be used for comparison? So, the comparison is generally done in terms of comparison of natural frequencies, model damping factors, mode shapes, and frequency response functions. So, let us first talk about mode shape correlation. So, the mode shape correlation involves comparing the mode shapes identified from the FE model with those from the model test. So, the pairing of the FE model and experimental mode shapes is necessary before the correlation between the natural frequencies and the damping factors can be quantified. So, here we see that we need to first find the pairs of the modes which correlate. For example, we should know that which mode from the FE correlates with a particular mode from the experimental set. So, this pairing of the modes, the correspondence between the modes from the FE model and the experiment needs to be first carried out, okay, and then only the comparison of natural frequencies and damping factors of these modes can be done, right, because we need to first identify which mode from the FE and which mode from the experimental set, they represent the same mode of vibration of the structure, and the comparison of the natural frequency and damping factors for these corresponding modes should be then done. So, that is why mode shape correlation is necessary before the correlation of natural frequency or modal damping factor can be carried out. One may argue that we can do the comparison of natural frequencies and damping factors by arranging the modes in the increasing order of their natural frequencies. We can arrange the FE model modes in the increasing order of the natural frequency, and the experimental modes also we can arrange, and then we can compare the modes corresponding to order in which they exist in the two sets. But this approach may not necessarily lead to the correct comparison, because the comparison based on their ascending order may not actually represent the same mode of vibration, right. For example, some modes in the experimental set might be missing because those modes were not excited in the model test or they were not measured. So, that will affect the order of the modes, right. Similarly, the sources of inaccuracies in the FE model, their magnitude determines the deviation of those frequencies obtained from the FE model, right. So, because of the inaccuracies, the natural frequencies may deviate and they may shuffle their order, right. So, that is why arranging the modes in the increasing order of natural frequency may not reveal the correct pairing between the modes from the experiment and the FE model. So, that is why it is first necessary to establish that pairing and then undertake the comparison of natural frequency and damping factors. So, how mode shape can be used for pairing of the modes? So, one approach which can be followed is based on visual comparison. For example, we can plot the mode shape from the FE model and the mode shapes identified from the experiment, right, and then we can do the comparison on a visual basis and see that which modes present the same mode of vibration. So, based on the distribution of the nodes and antinodes, so we can based on visual comparison determine which two modes correspond to each other or represent the same mode of vibration. So, this approach probably will work reasonably well for simpler structures like one dimensional structures or two dimensional structures like beams and plates. Visual comparison may help, but when the structure becomes complex, this visual comparison will be difficult to carry out to determine the pairing of the modes. Therefore, to address this problem, some indices have been suggested to quantify mode shape correlation. Modal assurance criteria, which is abbreviated as MAC, and this MAC between an experimental mode and an analytical mode is computed using this expression. So, you can see on the left hand side, this represents the MAC or the modal assurance criteria between analytical mode or FE model mode and the experimental mode. So, here subscript A is used to represent the analytical or FE model quantity, and subscript X is used to represent its association with the experiment or model test. So, this MAC value is computed by the expression shown on the right hand side. So, the numerator of this expression consists of the square of the magnitude of the dot product between the FE model mode shape and the experimental mode shape. And here Hermitian transpose is used to take the dot product, because in general the mode shapes could be complex. And then the denominator is a scaling factor. It consists of product of two quantities which are scalars. So, the first quantity is the dot product of the FE model mode with itself, right. So, this is that quantity, and the second is the dot product of experimental mode with itself. So, this is how the MAC value is defined and is computed. So, one thing we should note, it does not require either the mass matrix or stiffness matrix of the structure for computation. It is based purely on the mode shape from the FE and the experiment, and its value MAC lies from 0 to 1. So, the maximum value of MAC is 1 and the minimum value could be 0. The MAC value close to 1 indicates a good correlation between the two modes, while a value close to 0 indicates a poor correlation. So, we see that if the two modes are identical, right. So, phi A is identical to phi x, then this MAC would give value 1, and if there is any small deviation, then this value will drop below 1. So, larger the drop from 1, larger is the lack of correlation between the two mode shapes. Okay. So, this provides a very good index to quantify the degree of similarity between the two eigenvectors or two mode shapes. So, one advantage of this MAC is that no expansion or reduction is required, right. So, the cross orthogonality check required either the expansion of the measured mode shapes or model reduction of the FE model, but here no such expansion or reduction is required. That is because in computing this MAC, we would use only those DOFs in the FE model mode shapes which are corresponding to the DOFs in the experimental mode, right. So, that is why all the DOFs which are not measured in the experiment, they are dropped from the FE model eigenvector, and that truncated eigenvector is then used to compute the MAC value. Therefore, addressing the incompleteness of the mode shapes coming from experiment is very straightforward in computing the MAC, right. So, therefore, MAC is widely used for quantifying the correlation between the two mode shapes. So, with MAC, how do you obtain the pairing of modes and how does it indicate the degree of correlation? So, if let us say there are n modes corresponding to the FE model, and if there are small m number of modes corresponding to the experiment, then we can find a MAC matrix which is of order n by m. So, we can find MAC value between every FE and every experimental mode, that would give us a MAC matrix of size n by m. So, let us look at the first row of this MAC matrix. So, the first row of MAC matrix tells us the MAC correlation between the first FE mode and all the experimental modes. So, we expect all these values to change in the range from 0 to 1. So, whichever value is maximum, let us suppose the kth element in the first row is maximum, let us say something like say 0.9. So, that indicates that the kth mode from the experiment pairs with the first mode from the FE. So, this establishes the pairing of the mode, which indicates that the first mode from the finite element model and the kth mode from the experiment, they represent the same mode of vibration, right. So, this establishes the correlated mode pair, and then the question is how much correlation is there. So, the value of MAC indicates the degree of correlation, right. So, 0.9 indicates that there is a 90% similarity between the first FE mode and the kth experimental mode, correct. So, therefore, the MAC matrix does both the jobs. It not only allows pairing of the mode, but also allows quantifying the degree of correlation between those modes, right. And then we can go to the next row and next row and next row, and for each row in this way we can determine which FE mode pairs with which experimental mode, and also find the degree of correlation between the modes making up that pair. So, once mode shape correlation is established, now we exactly know which mode from FE and which mode from experiment, they represent the same mode of vibration of the structure, right. And now then we are in a position to compare the natural frequencies and modal damping factors corresponding to those modes. So, therefore, now we take the correlation of natural frequencies and damping factors. So, now we can find the difference between the natural frequencies of the analytical and experimental modes in each mode pair. We can determine the percentage error in the natural frequency predicted by the FE model, right. So, maybe we can take the difference of FE model neck frequency and experimental natural frequency and divide it by experimental natural frequency multiplied by 100, giving us the percentage error in the prediction made by the FE model, right. Similarly, we can find the difference between the damping factors of the analytical and experimental modes in each mode pair and determine the percentage error in the predictions of model damping factors based on the FE model. So, another correlation that can be done is the correlation of FRFs, so frequency response functions. So, frequency response function correlation does not require a prior correlation of mode shapes, natural frequencies or damping factors. So, that can be done independently of those correlations. So, here then we can overlay the FRF obtained from the experiment with the corresponding FRF from the FE model. So, for example, if we have let us say measured FRF alpha jk, right, which represents the FRF measured at jth degree of freedom with the excitation applied at the kth degree of freedom. So, that FRF we can also compute from the finite element model, and these two FRFs we can then overlay, which then would clearly indicate that to what extent the FE model FRF matches with the FRF measured in the model test. So, this overlay can be done for magnitude of the FRF and the phase of the FRF separately, and this FRF comparison gives at a glance the comparison of the frequency response over the complete frequency range of measurement. So, we would be able to see that how the peaks in the FE model FRF, how do they match with the peaks, right, resonant peaks in the experiment. We can also see how the anti-resonance pattern in the FE model FRF, how does it correlate or match with the anti-resonances in the experimental FRF. So, it gives at a glance a complete comparison over the frequency range of measurement, right, corresponding to degrees of freedom corresponding to the FRFs being compared. So, once the correlation of the FE model with the model test result is established, the question is what do we say about the validity of the FE model? Can we use it for the intended application? Because the percentage error, it may be small, it may be large. The question is how much error is tolerable. So, that depends upon the criteria of acceptable error in the FE model predictions, right. So, we need to decide how much error in the prediction can be accepted. So, that depends on for what application the FE model is intended to be used. So, for some applications the error that can be tolerated may be higher, for some applications the error that can be tolerated may be lower, right. For example, let us say we want to use the FE model to predict the response of the structure to a broadband excitation, is not it, and generally when the broadband excitation is there, the deviation in the predicted natural frequency by the FE model, that deviation will not cause a very large change in the dynamic response, because the excitation is broadband. So, for such application probably a higher level of error in the predictions may be tolerated, and acceptable criteria of error may not be so stringent, right. But let us say our objective is to predict the resonant frequencies of the structure using the FE model, correct. So, that the resonance during operation can be avoided. Now, for predicting the resonant frequencies, the FE model prediction should be good, because then only the resonances can be avoided, right. So, let us say if a harmonic force is acting on the structure and the frequency of the force is specified. So, now if the FE model cannot predict the resonance frequencies accurately, then we would not be able to reach to a definitive conclusion about whether the resonance would occur or not occur, right. So, in this application therefore, the acceptable criteria will have to be more stringent. So, therefore, the acceptable level of correlation, how much can be tolerated and how much cannot be tolerated, that depends on what kind of application for which the FE model has to be used. So, now we are going to talk about model reduction and mode shape expansion. So, we see that in FE model correlation and updating, the model reduction may be required to achieve consistency between the order of the experimental mode shapes and the FE model matrices. In updating, which we will study later, there also some methods may require this consistency to be resolved before updating can be carried out. So, therefore, we are now going to talk about some of the methods of model reduction and one method for mode shape expansion, to see that how this inconsistency can be resolved. So, let us look at Guyan reduction. So, this is one of the first techniques which were proposed for reducing the size of an FE model. So, this technique is based on dividing the all the DOFs into two sets. One is the master DOFs and other is a set of slave DOFs. So, master DOFs, they will be retained in the reduced model, while the slave DOFs will be eliminated in the process of reduction. Let us try to look at the formulation of this model reduction technique. So, the equation of motion for a undamped system subjected to external forces is given by this equation. So, where m and k are the mass and stiffness matrices of the system and f is the vector of forces. So, now in the Guyan reduction, we first decide what are the master DOFs and what are the slave DOFs, and how slave DOFs are chosen we will shortly see that. We therefore partition the vector of displacements into two parts. One is the vector of master DOFs and other is the vector of slave DOFs. So, xm is the vector of master DOFs and xs is the vector of slave DOFs. And then we also partition the equations of motion using this master and slave DOFs. So, you can see the mass matrix is also partitioned according to master and slave DOFs, and the stiffness matrix is also partitioned, and the force vector is also partitioned, right, corresponding to master and slave DOFs. Let us now consider the equilibrium corresponding to slave DOFs. So, this equation matrix equation is extracted from this equation only, right, corresponding to the slave DOFs. So, we expand all these matrices, then the equation corresponding to slave DOFs can be identified, which is this equation. So, in Guyan reduction, the slave DOFs are chosen based on two conditions. Those DOFs should not have any external force acting on them, right, and the inertia force associated with those DOFs should be small. So, any DOFs which do not have the external forces acting on them and the inertia forces associated with those DOFs is small or negligible, those DOFs qualify as being considered as slave DOFs. So, when the inertia force is small, the first two terms in this equation, you can see these are the two terms which are basically indicating the inertia forces associated with the slave DOFs. So, therefore, these two terms would be then negligible, and therefore, they are dropped. And then also the right hand side vector, which indicates the vector of forces on the slave DOFs, because the slave DOFs are chosen with no external forces, this vector also would be 0, right, and that is why this equation can be then approximately written in this form, ksm into xm plus kss into xs is equal to 0. So, this equation you see, it represents the static equilibrium at the slave DOFs. It represents equilibrium of the elastic forces corresponding to the slave DOFs, and that is why this indicates static equilibrium at the slave DOFs, right. and that is why this Guyan reduction technique is also basically called static condensation technique. So, from this equation now we can write xs is equal to minus inverse of kss into ksm into xm. So, this equation relates the slave degrees of freedom, the displacement at the slave degrees of freedom with the displacement at the master degrees of freedom. So, you can see these two degrees of freedom are related by the matrix minus inverse of kss into ksm. So, therefore, we can write down the vector of all DOFs x is as t times xm. So, when you substitute xs in the equation for x, we get this equation which transforms the complete vector of dx into vector of master DOFs. So, in this way we obtain a relationship between the displacement vector x and the displacement vector xm. Now, we substitute this equation into the equations of motion and we pre-multiplied by T transpose. So, when that is done, we get this equation for the reduced model. So, this is the equation of motion for the reduced model, where Mr and Kr are the reduced mass and stiffness matrices and Fr is the reduced force vector, which are given by Mr is equal to T transpose Mt, Kr is equal to T transpose Kt and Fr is equal to T transpose F, which basically is equal to vector of forces at the master degrees of freedom. So, this reduced system of equation has an order smaller than the order of the original equations, and that is how the reduction is realized. So, this technique is also called static reduction technique, because it determines the relationship between the slave DOFs and the master DOFs by considering static equilibrium at the slave DOFs. This is equivalent to saying that the dynamic equilibrium at the slave DOFs is considered by taking frequency omega equal to 0, right. So, if you write dynamic equilibrium at slave DOFs at frequency omega equal to 0, we get the equations of static equilibrium corresponding to slave DOFs. So, there is a variation of this technique in the terms of dynamic reduction. So, dynamic reduction technique is a modification of the Guyan reduction technique. So, here the dynamic equilibrium at the slave DOFs is not considered at omega equal to 0, but it is considered at a frequency omega equal to omega naught, right. So, omega naught can be chosen. So, therefore, if we write the dynamic equilibrium at the slave DOFs at omega equal to omega 0, we get this equation, right. So, here we see that now the inertia forces at the slave DOFs corresponding to frequency omega equal to 0, they are taken into account, right. And when this equation is simplified, we get this equation relating the vector of degrees of freedom and the vector of master DOFs. So, this transformation matrix now is a different transformation matrix than we got for the static reduction case. But we can easily see that if we take omega naught is equal to 0 here, then this transformation matrix reduces to the transformation matrix we got for the Guyan reduction, right. So, now by substituting this equation for x in the equations of motion, we can obtain the reduced mass and stiffness matrices and reduced force vector, like we obtained in case of the static reduction or the Guyan reduction. So, now these two techniques, they do not preserve the frequencies and the mode shapes of the original equation, right. They would undergo some change because of the model reduction and approximations being carried out. So, another technique for model reduction was developed whose objective was to preserve the natural frequencies and mode shapes of the selected modes in the reduced model, and that technique is system equivalent reduction expansion process, which is abbreviated as SERAP or acronymed as SERAP. And so, this preserves in the reduced model the natural frequencies and mode shapes of the selected modes of the original model. So, let us consider the equation of motion for the free vibration of an undamped system mx double dot plus kx equal to 0. And now this technique involves transformation of the displacement coordinates x into modal coordinates y, okay, using the p selected modes. So, you can see here x is the vector of degrees of freedom of the original model and phi is the matrix of mode shapes corresponding to the p modes that are to be preserved in the reduced model. That is why it is of order n by p, and y is the vector of modal responses corresponding to the p chosen modes, right. So, it is of order p by 1. So, P is the number of modes that are chosen which need to be preserved or which we want to preserve in the reduced model. Now, again we partition this vector x into two parts, the vector of master DOFs and vector of slave DOFs, and the eigenvector matrix is also partitioned accordingly into phi m and phi s, right. And now we can write down the equation for only the master degrees of freedom, right. So, that is x m is equal to phi m into y. So, here A is the number of master degrees of freedom, right. So, this is now you can see it is a system of linear equations, it is a system of linear equations. So, here if we choose A to be more than P, that is the number of master coordinates, they are more than the number of modes P, then this forms an overdetermined system of linear equations, and we can obtain a least square solution of this equation by taking the pseudo inverse of matrix phi m. So, that is why we obtain, now here you can see this is the solution for model responses y, right, which is equal to pseudo inverse of phi m into x m, and now this y model response vector is substituted into the model transformation we did, which was x is equal to phi y. So, this gives us the relationship between the vector x and vector x m, correct, and T is the transformation matrix, which is given by this product of matrix phi and the pseudo inverse of phi m. So, by substituting this vector x in the equations of motion and pre-multiplying by T transpose, we obtained a reduced mass and stiffness matrices for the reduced system of equations. So, as we said, to obtain a meaningful estimate of the model responses, P must be less than or equal to A. So, the number of master coordinates should be more than the number of modes P, so that the model responses which are estimated from the linear equations in the model transformation, they give a reasonable accurate estimate of the model responses. So, this syrup method was also formulated to expand the mode shapes, and so let us see how mode shape expansion can be done using syrup. So, this method requires only the FE model mode shapes or analytical mode shapes for expansion. So, the basic principle of this method is to express the measured mode shape as a linear combination of the FE model mode shapes. So, here the subscript m is used to represent the measured degrees of freedom, right, which are measured in the experimental mode shapes, and then subscript u we will use to represent those degrees of freedom in the FE model which have not been measured in the experiment. Subscript x is used to represent association with the experiment, while subscript a is used to indicate association with the FE model. So, that is why here phi mx represents the experimental mode shape at the measured degrees of freedom, and phi maj it represents the FE model mode shape corresponding to measured coordinates, right, and j is the mode shape number, the FE model mode shape number, right, and Cj is the coefficient corresponding to the jth FE model mode shape. This equation therefore is phi mx is equal to matrix phi ma into C. So, vector C is the vector of coefficients which indicate the way the different FE model mode shapes are combined linearly in order to obtain the experimental mode shape. So, from this equation we now find out what is vector of coefficient C, right, and that is given by the pseudo inverse of phi ma multiplied by vector phi mx. And now what we do? We use this vector of coefficient C in order to construct the unmeasured elements of the experimental mode shapes using the unmeasured elements of the FE model mode shapes. So, you can see here now we combine the unmeasured elements of the FE model mode shapes using this coefficient vector C to obtain the unmeasured elements of the experimental mode shapes. So, in this way we obtained a experimental vector with all the DOFs. So, this phi x contains not only the measured degrees of freedom, but also the unmeasured degrees of freedom. So, in this way the experimental mode shapes are expanded to the size of the FE model. So, in this way we come to the end of this lecture. So, in this lecture we have studied what is FE model validation, what is the need of FE model validation, how correlation of the FE model is carried out with the model test results, and then we looked at some indices for FE model correlation, and we also talked about model reduction and mod shape expansion. Thank you.